Hi everyone and welcome to a new video about noise analysis in RC circuits. This is our example number 4 of a noise analysis and actually our second example of a RC circuit. And again we will look at calculations step by step and we will verify these in SPICE simulations. So let's look at our example. We have the following situation. We have two resistors R1 and R2 given in this circuit, and we have some capacitor values, in this case 4 different capacitor values. So we have actually a voltage divider of two resistors, and we have a capacitor which is then in parallel with that second resistor of 3 kilo ohms. We have the output voltage at this node, and we have an input voltage Vin, which is then our AC input voltage. So two resistors and one capacitor, and the capacitor value will change from 0 to 1 picofarads to 1 nanovarads and 1 microfarads, and we will then carry out the calculations for each case for the capacitor. So for each capacitor value, calculate the output noise voltage spectral density. That is the question A. B is the input noise voltage spectral density, and for C we would like to have the total RMS output noise voltage. And for D, the final one, is the signal to noise ratio SNR. These are the 4 what we need for these 4 cases of the capacitor. So let's look at our solutions. How do you start? As we did in the previous example, we'll disable all the independent sources. In this case we have only one voltage source, so that will be a short. If this were a current source, it will be an open circuit. Now again, a very short summary for thermal noise power spectral density is given in general form by this expression. You can see the square here that will emphasize the noise power. And if you go from there to the noise voltage spectral density, you will take the square root of this expression. Then you will have the small letter e sub n, and that will be the square root of that 4 key TR. And that will be the units for the noise voltage spectral density. Now for the thermal noise voltage spectral density, for this RC circuit specifically, is then given in general by this expression. Now we need, of course, a little bit careful by using this formula. If you only have a pure RC circuit, you can use this formula. If you have a different circuit, then you still need this formula if it is a pure resistive circuit. But what is really interesting here is that there is no resistor in this expression, which is really interesting, and we will see why this is happening, and we will also prove this using simulations. Now again, the parameters in summary here, the K was the Boltzmann's constant, so it has a value approximately of 1.38 times 10 to the power minus 23 joules per Kelvin. The T is the temperature, in this case the absolute temperature given in kelvins, and for room temperature operation, let's say 27 degrees, the T will be approximately 300 Kelvin. The R is the equivalent resistance seen at a node given in ohms. So for example at this node, if you're interested in the output. And the C is the capacitor value in farads. So that's actually the capacitor we have in our circuit. But let's look at the noise in our RC circuit in more detail again. A reactive component can be a capacitor or an inductor, in this case a capacitor, does not produce a noise in ideal case. So when combined with a resistor, the thermal noise does depend then on the value of the resistance. So it is really dependent on what we have as a circuit. So if you have an RC circuit, which is just so if you have an RC circuit, as I said before, just having pure R, pure C in ideal case, then the thermal noise voltage will not depend on the value of the resistor if it is in combination. So if I have a large resistance and if I'll make it larger, I will generate more noise. That is also seen from this expression. But if I also have a large resistance, that will also reduce my bandwidth. So in one case I will generate more noise, and I will again make this resistance more, but it will reduce also my bandwidth. So both effects, more noise and also in the bandwidth, will cancel each other out. Why? Let's see in more detail why this is happening. The signal bandwidth, the bandwidth of our circuit, is given by this expression, which is then 1 over 2 pi RC, which is in general. This R is of course the thevenin resistance seen by this capacitor, which is then, in this case, by shorting this out, you will have R1 in parallel with R2. But if you also look at the noise bandwidth, which is then of course the actual bandwidth we need to consider, you need to make a conversion from the signal bandwidth to the noise bandwidth, which has a conversion factor of pi over 2, which is 0.5 times pi. So if you multiply this by pi over 2, you will have then the noise bandwidth for this RC circuit of 1 over 4 RC. Again, this R is the thevenin resistance seen by this capacitor, which is then the combined parallel combination of the R1 and R2. In this case, if you do the math very quickly, it will be 750 ohms. Now, let's look at the RMS noise voltage, which will be given by this expression. So it has a value of volts in RMS, and that will be the noise voltage spectral density times the square root of that noise bandwidth. So this E sub n is given here, and the noise bandwidth is shown here. So if I now substitute those values, so I have the square root of 4k TR, and I have the square root of 1 over the 4 RC. Again, these two R's are the thevenin resistances seen between the nodes of my capacitor, which is the parallel combination of R1 and R2. Then I have, by simplifying this, and if I now see this expression, I can now divide out these two fours in the numerator and denominator, and also the R, so I will have a simplified expression, which is then given by square root of K times T over C, which is then now in RMS. So this proves that the RMS noise voltage of this, the output, is independent of the value of the resistance. So that's really interesting. So let's look at it in more detail, step by step, and also determine these 4 elements in our example. Now, let's start with the output noise voltage spectral density. For the case where the capacitor is 0 farads, that means actually the capacitor is actually effectively an open. That means then the circuit will then reduce the voltage divider, consisting of only R1 and R2. Then you will have an output noise voltage spectral density of 3.525 nanovolts per root hertz. We have done this in more detail already in example number 1 about a pure resistive circuit having only R1 and R2, where the R1 was 1 kilo ohm and R2 was 3 kilo ohm. So you can look at example number 1 in the video series about noise analysis. Now, if I make this capacitor 1 picofarads, also really small, then I can use this formula for my output noise voltage spectral density, which is just substitute the values for the K and the T for the temperature of 300 kelvins and for capacitor 10 to the power minus 12. And I will do the math, you will get 64.36 microvolts per root hertz. Now, similar for 1 nanofarads, so I will have then 2.035 microvolts per root hertz, and in similar form I did for 1 microfarad, so 1 pico, 1 nano, 1 micro, and I will have this value. So that will be now in nanovolts, so 64.36 nanovolts per root hertz. Now, if I combine these results for 0 farads, 1 pico, 1 nano, 1 micro, I will have these results. Again, this result for 0 farad, that means actually an open circuit for the capacitor. That is just the circuit where you have only 2 resistors, and that is just the voltage divider circuit. So the capacitor effect will not be there, so you cannot use this formula actually in the case where we have the capacitor 0 farads. So the input noise voltage spectral density, then the capacitor is on its own does not produce noise. We already said that. The input noise voltage spectral density will be only caused by the resistors. because we only look at the input, not the output. So that's really important to see here. So excluding the effect of the capacitor, the signal gain, which is the gain actually from input to the output, is given by the voltage divider rule, which is then the R2 over R1 plus R2, which is then 3 kilo ohms over 4 kilo ohms, which is then 3 over 4, 0.75. So it's using signal gain and also the output noise voltage spectral density. We already did this. We can now calculate the total input noise voltage spectral density, which is just, of course, the output is the signal, the gain times the input noise. So in this case, of course, we use the signal gain. Well, to be precise, we need to use the noise gain, and it will be, of course, much more important when we have active circuits like an op-amp circuit. So in this case, it doesn't really matter because you have this, still the noise gain and the signal gain are equal to each other, but in precise terms, you really need to use the noise gain. Okay, so this is the expression, just output is equal to the gain times the input, like that. So the output noise is equal to the gain times the input noise. And if I rewrite this to have the input noise spectral density, I have then the output noise voltage spectral density divided by the gain. I will now have 4.7 approximately nanovolts per root hertz. Note, this is really important, you might think, okay, I have now the formula for my input noise voltage spectral density, so I can move on, also do the math for the rest of the values, because I know this is then the output noise spectral density for the case where there is no capacitor, so actually 0 farads. But if I go to 1 picofarad, this was the output noise voltage spectral density, then I will then say, okay, let's then divide this also by 3 over 4, because I did it also here. But the thing is, you look at the input, not the output, so the filtering effect will not be present at the input, it will be only at the output. So it is not that the value will be then this over 3 over 5, then you have this, 3 over 4 I mean. This value will not be divided by 3 over 4, and also not this one and also not that one. So these three values you don't have, you only have the 4.7 nanovolts per root hertz as your input noise voltage spectral density. That will be the case actually for all cases for the input. That means the input noise voltage spectral density will be constant, and that will be just 4.7 nanovolts per root hertz in this case. We will see that also in the simulation, so wait for that, such that you also see that in the simulation. Okay, let's also look at the total RMS output noise voltage, because that's really important for this circuit. We know the total RMS output noise voltage is independent of the bandwidth if we have filtering. Because if you have a filtering, that will have some independency due to that action with the capacitor and the resistor. That's actually the action of filtering. So the total RMS output noise voltage depends on the capacitor value only. We already seen that by looking at this formula, kT over C, the square root of that one, the ratio. Okay, now again, for capacitor value of 0, that means we have then a capacitor which is effectively open. That circuit again reduces to a voltage divider rule. You can see already here again that we have the R2 over R1 plus R2, and then we have the situation we already discussed. So the total RMS output noise voltage will increase without a limit as the frequency band is increased. Why? Because there's no filtering, so there's no filter action due to the reactive component, in this case the capacitor. So when the frequency band is increasing, you will have an increasing noise RMS value at the output. Why? Because the formula we have here does not hold, because there is no capacitor, and this is the formula actually we have. In this case, the 4 kT times the thevenin resistance times the noise bandwidth, and then square root of that value. That will be then the RMS value at the output as the volts. Now, we can of course substitute the values, and the thevenin resistance is just the parallel combination of these R1 and R2, which is then 750, but the noise bandwidth will increase. And that will of course increase. Let's say it started at 1 Hertz, then it goes to 10 Hertz, then it goes to 1 kilo, 10 kilo, 1 mega, etc. But since this will be increasing, this will never reach a steady value. So it will also approach infinity. And we have, of course, seen these also in example number 1 in the video, so we can look at that for more details. But this is a really important point here for a capacitor of 0 value. If you have a capacitor of 1 picofarad, so that is some filtering, then we can use this formula, and then you substitute the value, you will have 64.36 microvolts in RMS. Now, if you move on for 1 nanofarads, you do the math again, you will have this value, and for 1 microfarad, you will have this value. And if you now collect these all in a table, you can see what happens for 0 farads. It will increases without a limit. But for 1 pico, 1 nano, 1 micro, there is some filtering. You can see what the values are for total RMS output noise voltage, given here in volts RMS. So that's actually our observation for calculations for our total RMS output noise voltage. Okay, let's then move to the next step, which is then the signal to noise ratio, SNR. Again, in summary, signal to noise ratio is a measure that compares the desired signal to the noise level. It has actually a ratio, but specifically the power. So we need to make the ratio of the signal power to the noise power, and that is often expressed in units of decibels, so dBs for short. A ratio higher than 1 means that you have more signal than noise, and if you have a ratio which is between 0 and 1, that means actually you have less signal than noise. That means noise is larger than the signal. And in dBs, that means if you have more signal than noise, you have a value which is larger than 0, and if you have more noise than the signal, you have a value which is then negative, so it is then less than 0 in dBs. Now, for this circuit, the SNR at the output for a specific frequency can be calculated using this formula. We will see how we can do that. Let's again remember what we had for our total output RMS noise voltage, because that is the parameter we have in our SNR formula, because this formula will give you the SNR in dBs. Now, I look at 0, 1 picofarad, 1 nanofarad, and 1 microfarad, and I will these are the results. And if I now calculate this for each case for the capacitors, excluding this one, I have then the following table. So 1 pico, 1 nano, and 1 micro. You can see I have then different SNRs for specific capacitors. So the capacitor will have effect on the SNR. So in conclusion, we can say the following. The SNR is independent of the resistor value, but it is dependent on the capacitor value. It increases as the capacitor value is increasing. So if I go from 1 pico to 1 nano, if I'm from nano to 1 micro, so it will increase actually, then this will also increase. Why? Because you have the more filtering. That means you filter out more noise. So your signal level is then larger in ratio compared to the noise level. But your RMS noise voltage at the output will decrease as the capacitor is increasing, which is of course straightforward, because then you have more filtering by increasing your capacitor value, so you will decrease your noise. So it is also really straightforward. Okay, let's look at the simulation result, starting with input noise voltage spectral density. As I said before, you can see that for different cases for the capacitor, this is the red one, this is the blue one. So red one is actually for the capacitor is 0, 1 picofarads for the blue one, 1 nanofarad for the pink one, and 1 microfarad for the dark blue one. You can see that the value for each of these capacitors is 4.7 nanovolts per root hertz for all capacitors. So actually, input noise voltage spectral density is constant, as we have discussed. It is not that we need to divide that by the signal gain for each capacitor value. It is just this circuit without the capacitor, because you look at the input and you don't take into account or use the filtering at the output. That is an important point here. So this is again a confirmation. Let's also look at the frequency response, specifically bandwidth. And for that, of course, we will make a Bode diagram. This is the body plot or body diagram I have generated specifically for the gain, so the magnitude. The DC gain here, you can see for all cases, is minus 2.5 dB. It is very easy to see that. How can we see this? The capacitor will be an open circuit for DC. Then you have, of course, some attenuation, just a voltage divider rule, which will be always 3 over 4. So it will be 3000 over 4000. And if you then do 20 log of that 0.45, 3 over 4, you will have very close to minus 2.5 dB. So you will start at that value. Now, if I look at different capacitor values, for 1 microfarad, 1 nanofarad, and 1 picofarad, you can see the cutoff frequencies will be also given here. 212 for 212 hertz for 1 microfarad, 212 kilohertz, so 1 nanofarad, and it will be 212 megahertz for 1 picofarad. So if I decrease the decrease the capacitor, I will increase my cutoff frequency, in this case increase my bandwidth. So this is also given here, and I will of course use the thevenin resistance of 750 ohms, because the capacitor will then see these two resistors in parallel when I disable this AC input voltage. Now, if I do the math here for the cases 1 micro, 1 nano, 1 pico, you can then calculate for yourself, and these are also simulated. So that is the confirmation of the calculation, also the simulations. So let's also look at the output noise voltage spectral density. That plot is also shown here. It looks similar to a body diagram, but in this case I'm looking of course to the noise at the output, spectral density of course, and what you see is it is 3.53 nanovolts per root hertz for the case where the capacitor is 0. So there is no capacitor, just an open circuit. So actually the voltage divider rule here. Now if I look at the capacitor for 1 micro, 1 nano, 1 pico, you can see again the cutoff frequency for each capacitor, which is then also seen in our body diagram. And this is again very straightforward result, and it confirms actually what we had for the output noise spectral density. But this will of course have some effect, also effect of the bandwidth. So this will be then seen later on in our total output noise voltage. And this is again the cutoff frequencies for each capacitor. Now, this is very important, the total RMS output noise voltage, what will then happen there. Again, this is the situation where the red one is the situation where the capacitor is 0. That means we have a voltage divider by 2 resistors. You can see the value of the output noise, total noise, will increase without a limit. So if I increase the frequency, I will increase with my noise. That is again straightforward because there is no filtering. So by increasing the noise bandwidth or your frequency range, you will increase your noise, so that will just increase without a limit. But if I have filtering for example the blue one, which is then for 1 picofarads, I will then approach a value of 64.33 microvolts RMS in this case. For 1 nano, I will approach here 2.04 microvolts, and for the green one, which is then for 1 microfarads, I will approach 64.36 nanovolts RMS. You can see again, increasing the frequency, increasing capacitor, will decrease your value of your output noise voltage RMS, because this is of course larger than that one, and this is of course much smaller than that one, so it will decrease. And again, total RMS output noise voltage depends on the capacitor value, and it will decrease by increasing the capacitor. It will not decrease or change due to the resistor values, only for the first case where we don't have of course the capacitor, but that is just a special case. Okay, let's also look at the signal noise ratio SNR for our circuits again. Again, the first one was the red one, which is then the capacitor of 0, which is again open here, so we only have 2 resistors, again the voltage divider, and that is this line, which will of course start at a very large value for very low frequencies, but it will go down and have actually a slope which is just still decreasing in the SNR, but it keeps decreasing as the frequency moves on. It will decrease as the frequency increases, and we have seen this also in the noise plot for the output total RMS value. So by seeing that the total RMS value for the capacitor of 0 farads will increase, your SNR will of course also decrease. So that is actually a very logical consequence of that one. If I look at the 1 picofarad, which is the blue one for a capacitor of 1 pico, I see it is now 83.9 approximately dB. But if I now increase this capacitor by a factor of 1000, 1 nanofarads, I will now approach an SNR of 113.8 dB. And if I now again increase the capacitor value by a factor of 1000, make it 1 microfarad, that will be, for the green one, that will be 143.8 dBs. So the SNR, again, the formula is of course calculated by this, and we have now the table here in summary. These are the calculations for each capacitor. So this is the total RMS noise voltage, and if you do the math here, just substitute in here in this formula, you will get these results, and these are very close to what we have here. And for some of them are exactly equal to each other. So that is a very nice result. And again, in summary here, we can say the conclusion, SNR is independent of the resistor value. It will depend on the capacitor value. It is increasing as the capacitor is increasing. So we have already seen this. So more filtering means more signal to noise ratio. That means we have more signal than the noise, so the ratio is larger. And if you, of course, have a capacitor which is increasing, you will also decrease your output noise voltage RMS, which is really understandable from the fact that we have more filtering. Okay, that is now, these are the results for our simulation. We can now look at the simulation also in SPICE and see the situation and how we can generate these plots also there. So let's jump to SPICE. Now we are now at the SPICE simulator. I have now my circuit here with the R1 and R2 and a capacitor in parallel with R1, R2. This is the output voltage where we measure the output across the capacitor and also across the resistor R2, and this is our input voltage Vin. As I already explained in the previous videos, this must be just an AC voltage source. It doesn't matter what you take here. It can be a square, can be a step, anything, but just AC voltage source. Okay, R1 was 1 kilo, R2 was 3 kilo, and the capacitor here has an asterisk because we have 4 cases. So if I look at the control object and click on it, I already prepared this, and I go to the list I made here. You can see the first parameter 0 farads, 1 pico, 1 nano, 1 micro. I can of course add a new one, or you can also say 1 milli. But then you have 5 cases, but now I have, of course, I'm interested in these 4 cases. So let's remove the last one and then say OK and then OK. So if I now generate the plots, I will get for each case the noise plots. Of course, I go to the analysis, as I did also before, the noise analysis, and I can now select my starting frequency, my end frequency, and also the number of points to have it accurate. I already found out that this is what you can get at max in this SPICE simulator. Now I have now several plots here. I can do output noise spectral density, input noise spectral density, total RMS output noise voltage, and also the signal to noise ratio. Now let's do all of them because we have also calculated those and see what we get. So let's run this and then OK and see what we get. Okay, it will take some time to generate the plots. Okay, we have now the plots here. Let's start with output noise voltage. You can see if I make the label, you can already see actually it starts at 3.53 nanovolts per root hertz. You can also see that from the units here. So that was also what we have calculated, but that's for this one. So let me also make the labels and make this a little bit larger. You can see that in great detail. So this is actually, if I now highlight this, just press on it to highlight it, so it's actually for 0 farads. If I highlight this one, That is for the 1 pico, so it has the largest cutoff frequency. And for that one is then for this one I mean, is the situation for 1 nano. So also a little bit less cutoff frequency. And this is actually the smallest cutoff frequency for 1 microfarads. So you can see they all start at 3.53 nanovolts per root hertz, but they will decrease if you have filtering. If you don't have filtering for this case, which is just a voltage divider circuit, then you will have a constant output noise voltage. Okay, let's also look at the input noise voltage. You can see actually there is no difference. It is actually 4.7 here, 4.7 here. I will do separate curves, then you will see what's happening. Then you will see actually that for each case you will have 4.7. I will increase this, and it's actually also the discussion we had. You don't divide out by the signal gain for each output noise spectral density. You will need to look at the input without taking into consideration the filtering at the output. That's why we have for each case here 4.7. So this one 4.7, you will highlight this. You can also see the highlight there for 0 farads. If I now highlight this one for 1 pico, it's still 4.7. For this one, for 1 nano, it's 4.7. And also for the next one, the 1 micro, it's also 4.7. So it's all 4.7 nano volts per root hertz. Okay, let's also look at the noise, total noise at the output, so total RMS noise voltage. You can see maybe also better to separate the curves here. So this is a total RMS noise. You can see actually in this case also, I will make this also larger and then highlight this one. This is the first case where you have actually no capacitor, 0 capacitor, and you can see that it is increasing without a limit when the frequency is increasing. If I look for the blue, I'm in the green line and I will highlight this here. That will be of course red if when I highlight this. For 1 picofarads, you can see it will approach a value of 64.33. I had 64.36 micro, so it's very close, maybe due to rounding of errors, but it is very nice to see that it is very close to what we have calculated. Now if I highlight this now for 1 nanofarad, I have 2.04 microvolts per root, I mean in RMS, and that's also in agreement with our calculations. And final one is for the case when we have microfarads, you can see it is also according to our calculations. Okay, now let's also look at the signal noise ratio. This is the signal to noise ratio plot. And I will place the label here and make it larger, a little bit more. Okay, this is then the line, the red line here, I highlighted again. For this one, where you don't have the capacitor again, the signal to noise ratio will decrease as the frequency is increasing. Okay, that is again according to our calculations. I will now highlight the second one, which is then for 1 picofarad, and you can see I can also make the label here. For example, let's make it at 10 gigahertz. And if I now again make the legend, here you can see also the values. So I can see, and if you of course just ignore this one because it's a specific value, but it will of course decrease. You can see that for 1 pico, this is actually for this one, it is 83.9 dB approximately, and which is actually what we had approximately. This is for 1 nanofarad. It was in our case 113.81 dB. Now it is very close to what we have here. And if I look at the 1 microfarad, I have 143.8 dB here approximately. So it's also very close to what we had. So this is all in confirmation with our calculations, and we of course discussed this in the simulation result also. But now we have also seen how to generate these plots also in SPICE, which is of course a little bit helpful when you need to do that by yourself. Okay, this was our example about another RC circuit where you see two resistors, so you have actually a voltage divider action with a capacitor at the output for filtering action. Of course, the calculations are not that difficult if you do that step by step in a straightforward manner. But what is really important is where you look at it, and if you look at the input, you don't consider the filtering. So that's actually one of the important messages from this example. All right, this is then the end of our example number 4. I hope this is in a different form, clarifying the problem or the analysis of a noise for active and reactive circuit where you have capacitors or an RC circuit and different RC circuit. If you have any questions, comments, please let me know, and I see you hopefully next time. And don't forget to share and like this video so that we can reach more people. See you next time and take care.